So far we know that a compound with zero chirality centers is achiral as long as there's a plane of symmetry. A compound with one chirality center will be chiral. That compound will have enantiomers. A compound with two chirality centers will have enantiomers, diastereomers, and maybe meso compounds. The maximum number of stereoisomers given by the 2 to the n rule, that is, a compound with n chirality centers can have a maximum 2 to the n stereoisomers. A compound with zero chirality centers is achiral as long as there's a plane of symmetry. So stop the video, draw the structures of these two compounds, and find the plane of symmetry. And here are the answers. The plane of symmetry is that red line, or another plane of symmetry could be this one. There is only one plane of symmetry for CH2ClBr. Stop the video again, draw the structure of this compound, and determine whether this compound is chiral. And the answer is, this compound is chiral because there is not a plane of symmetry. Let's review bonding in this compound, so stop the video and answer this question. And the answers are, here's the structure of tartaric acid, so stop the video and answer these questions. Tartaric acid is found in wine. Tartaric acid crystals are indicative of good quality. And here's a picture of a polarized light micrograph of tartaric acid crystals. Tartaric acid has two chirality centers, so it has 4 stereoisomers. The Fisher projection of the 4 stereoisomers are shown. For structure B, here's the configuration at each chirality center. So stop the video, identify which isomers are enantiomers, which are diastereomers, and is there a meso compound? And the answers are, B and D are meso compounds, which means B and D are meso compounds are achiral. That means B and D must have a plane of symmetry. Stop the video and find that plane of symmetry. So here are the plane of symmetries. Since structures B and D are the same, tartaric acid has 3 stereoisomers, not 4. Let's say you change the acid group on structures B and D to a methyl group. Do you still have a meso compound? Stop the video and answer that question. The answer is no, because there's no more plane of symmetry. Optical activity is a property of a substance, and it's the ability of that substance to rotate a plane of polarized light. For example, amino acids and sugars are classified as either D or L. D means the compound rotates a plane of polarized light in the clockwise direction. L means it rotates a plane of polarized light in the counterclockwise direction. Optical activity is measured by the specific rotation. Stop the video and answer this question. The answer is, polarimetry experiments show that naturally occurring RR tartaric acid, that's structure A, rotates a plane of polarized light plus 12.4 degrees. What is the specific rotation of the enantiomer of the RR tartaric acid? The answer is, stop the video and answer the 3 remaining questions. And the answers are, glucose and galactose are aldohexose sugars. Aldo meaning aldehyde and hexose meaning a 6-carbon sugar. So stop the video and answer these 3 questions. So glucose has 4 chirality centers, which means there are 16 maximum stereoisomers. And an enantiomer of glucose looks like, and 1 diastereomer of galactose looks like. A pheromone is a chemical released by one member of a species that triggers a behavior in another member of the same species. These 3 compounds are possible human pheromones. So stop the video and determine how many stereoisomers each compound has. So first determine the number of chirality centers in each compound, then apply the 2 to the n rule. Note that the wedges and dashes are a big hint that that's a chirality center. Here are some stereochemistry terms. We looked at a racemic mixture. The enantiomeric excess is 0% because 50% of the R minus 50% of the S equals 0. It is usually difficult to resolve a racemic mixture into its enantiomers. Erythro and threo are usually referred to sugars. And we will look at stereospecific reactions and stereoselective reactions later on. Let's say you want to separate a racemic mixture of these enantiomers using quinine. So stop the video and look at the structure of the reactants, quinine, and the products, and then fill in this blank and answer this question. Note that quinine has a chirality center, so, and for the question the answer is, so let's practice. Stop the video and identify the relationship in each of the following pairs. And the answers are